So, hello students, good afternoon to you all. So, students, can you hear me? Yeah. Good afternoon, Jyoti Kumari. Can you hear me? Okay, fine. So, coming to the class, so we are dealing with the general organic chemistry lesson, right? So, till last class, we have seen the isomerism part, IUPAC nomenclature part, and reagents in organic chemistry, those things we have discussed. And at last, we have completed with electronic displacement effects, right? Electronic displacement effects. And as I told you, there are three effects actually. So the first effect is inductive and the second is hyperconjugation. Third is your resonance effect and last one is aromaticity. That is a separate topic that will not come under this electron displacement effect. Okay. And among these three effects in the last class, I have discussed the inductive effect and hyperconjugation with you. So for today, we are going to start with the resonance or mesomeric effect. Okay. So before moving on to the definition or the information about the resonance effect, we should know what is resonance, right? We should know what is resonance first of all. So let us see what it is, then we will move on with the effect part, okay? So what is resonance? Resonance is the delocalization of pi electrons. Resonance is the delocalization of pi electrons, okay? So what are pi electrons? The electrons which are present in the pi bond. So how does a pi bond form? Due to the sideways overlap of the orbital. Due to the sideways overlap of the p orbital or d orbital, we get the pi bond, okay? And the electrons present in it are called as pi electrons. And usually resonance occurs in the planar structure only, okay? So the one which is having sp2 hybridized system, they will have a trigonal planar structure. In that case only, you can find the delocalization of pi electrons, okay? And the very common example for the system which is planar in structure is the benzene, okay? So how many carbons are there in benzene? We have 6 carbons, right? So 1, 2, 3, 4, 5 and 6. So C6, H6 is benzene and we have 6 carbons and all the carbons you can see they are double bonded carbon. So the hybridization of each carbon will be sp2. Okay. So there will be one electron present in the unhybridized p orbital. One electron will be there in the unhybridized p orbital. And this is the shape of p orbital, which is dumbbell in shape. And you can see that each carbon, you can see in this picture that each carbon is having p orbital, unhybridized p orbital with dumbbell shape, and one electron is present in all the cases. Okay. Now what happens? So there is a pi bond. There is a sideways overlap which you can see. There is a sideways overlap between the unhybridized p orbital of each carbon. Between two carbons, you can see that overlap. So through that only we'll get a pi bond. Got it? You can see the sigma bonds are present here. You can see the sigma bonds here. All the single bonds are sigma bonds. Okay. There are 6 carbon-carbon sigma bonds and 6 carbon-hydrogen sigma bond in it. Now these are the pi bonds. These are the pi bonds which is formed by the sideways overlap of the orbital. Okay. Now what happens? Now you can see in this picture. In the previous picture I have showed you that the pi electrons are between carbon 1 and 6, carbon 2 and 3 and carbon 5 and 4. Now you can see it is between carbon 1 and 2, 3 and 4 and 5 and 6. Okay. The representation, the bond line representation for this particular configuration is this. So what is happening here? What I have done? So the pi electron which is here, it is getting delocalized to this part and it is moving towards this position. It is going towards this position. So through this, we are getting this particular structure. And again, if you shift the pi electrons like this, you will get the first structure again. Okay. So this is nothing but the delocalization. Delocalization means moving from one place to another. Okay. So pi electrons are moving from one place to another, leading to the resonance. Got it? So this is otherwise called as this alternative double bond. This alternative double bond system we are getting, no? This is otherwise called as conjugation. It is otherwise called as conjugation. Okay. So it is called as conjugation. So this particular delocalization or the conjugation, it will not occur only in benzene. It will also occur in many types of systems. Okay. Now I am going to discuss with you those types of systems. Okay. It is not only with benzene, it will be with some other thing also. So the first condition or the first type of system you can see here is the open chain system, open chain carbon containing system, which has alternative pi bonds. Okay. So here what happens here, conjugation of pi bond occurs. So what is conjugation? Alternative. Okay. So now electrons are going like this, electrons are shifting. So here you can see the pi electron which is present here, it is shifting towards this sigma bond, and here delocalization happens. So the last pi bond, that pi electron is moving towards the last carbon. Okay. So because of this particular delocalization, we get another structure. We get a structure like this. So since this particular electron has moved to this position, we are getting a positive charge here because it is electron deficient. And here the electron rich nature increases, right? So we are getting a negative charge. Electrons are moving towards that current. Okay. Now what happens? Again, this electron can come here. This will go here and this will go here. So what I'll get the first structure back again. Got it? Now these two structures are called as resonance structures. These two structures are called as resonance structure. You can see the arrow which I have given. So it is a double-headed arrow. It is a double-headed arrow. Okay. So means both are resonance structures. Got it? So it is in the first type, you can see that the electrons are in alternative position and resonance exists in those cases. And coming to the second type is allylic cation. So in allylic cation also it exists. So what is meant by allyl? Allyl means it is a 3-carbon containing system. Allyl is a 3-carbon containing system with the one double bond and one single bond in it. Okay, now the carbon which is singly bonded, it will carry the positive charge. So now this system is called as allylic. So here H2 and here H and here you will have H2. So this is that. This is the bond line structure of the structure which I have drawn here. Okay, this is called as allylic system. Allylic means 3-carbon containing system with one double bond and another single bond in it. Got it? So allylic cation. So in allylic cation, how resonance occurs? The electrons which pi electron which is here, it will go here. So because of this electron shifting, one more structure is formed. So again, this will come back. So we will get the first structure again. Got it? So resonance exists in the conjugation of pi bond and it existing in the allylic cation. Okay. Then the third type of system is allylic anion. In allylic anion also you can see there is a shifting of pi electron. So how does it getting shifted? So the negative charge, this negative charge is moving towards this particular bond and the pi electrons which is located here, it is moving towards this carbon. Got it? So because of this, we are getting one more structure which you can see it on the screen. So what happens again? This pi electron comes back here and this goes back to this carbon to give the first structure again. Got it? So this is how resonance happens in allylic anion. Then coming to the fourth type, it is the allylic system which has lone pair. Allylic system which has lone pair also exhibit resonance. How does it exhibit resonance? The electrons which is there on the nitrogen, it will go towards the direction and the pi electron will move towards the carbon. So we get one more structure like this. And if you shift the electron back here and this electron back to the nitrogen, you will get the first structure again. So this is the fourth type. And the fifth type that exhibit the resonance is allylic radical. So in radical system, you can see one electron is moving towards that second carbon and third carbon. So one electron from the pi bond is shifting towards that. Okay. And the other electron is going to the first carbon. So we get a radical here and this system here. So again, what happens? This will come here and one of the electron will come here to form the pi bond there. And the one last electron will go back to the third carbon again to give the first structure. Got it? So these are the 5 types of systems which exhibit resonance. Got it? Now, next we will move on to the rules for drawing the resonance structure. So what are the rules we have to draw the resonance structure? So the first rule is all the structure must be in the Lewis form. All resonance structures must be the Lewis structure. Okay? And the next rule is always the electrons move from the more electron density region to the less electron density region. So in the previous cases also you might have seen that the in case of allylic lone pair, electron is moving from the lone pair to the other system, right? So always the electron moves from the higher electron density region to lower electron density region. This is the first step, second rule. And the third rule is only electron moves, not the atoms. Got it? So in a structure, only electron moves from one place to another, not the atoms. So you can see in the structure, that this particular hydrogen atom is moving towards this position. It is going and forming the bond with oxygen. So here who is moving? Here hydrogen is moving. Got it? So this is not called as resonance. This is not called as resonance. So what is meant by electronic movement? How does an electron move? So in the previous cases we have seen, no. So from that I have put one thing as an example for you. So here who is moving? Only the electron is moving from a particular atom to the another atom. That is bond to bond shifting is there. Bond pair of electron, you can see it is moving from one place to another. And bond to atom. And the third case is atom to bond. From nitrogen atom to the other bond, it is moving. Got it? So only the electrons move and not the atoms. Got it? Electrons will move from atom to atom. Atom will not move. Got it? So these are the rules. And one more rule also we have. The number of unpaired electrons in all the resonating structure must be same. Number of unpaired electron in all the resonance structure must be same. So these are the 5 rules which we have to follow to draw the resonance structure. Got it? So what is the first one? All must be in the loose structured form, and electron always move from higher density to lower electron density region. Only the electron moves and not the atoms. Okay? And the last one is the number of unpaired electrons in all the resonating structure must be same. Got it? So now let us do one question. So if you have any doubt, you can ask me. Any doubt, students? So far from the part which we have discussed? So today you guys have joined late. What is the reason? Any issues for all? Yeah, Jyoti Kumari, I'll repeat the second point. But I just want a particular thing from you, answer from you all that what happened today? Why you guys have joined late? You didn't get the information about the today's class, or some other test or something is going on in your schools? Can anyone reply me regarding this? Unfortunately, you joined in physics class. Okay. Okay. What about others? Usually, you guys used to join before 3 o'clock to chemistry class, no? But today, you guys have joined very late. What happened? Anjanasri, good afternoon. Priyanka, Rajesh, Mamta. The other one from Samsung Lab too, huh? Okay. Try to join on time every day. That is from Monday, Tuesday, and Thursday, Friday, we are having class, no? Try to join on time so that you will not miss any part. Okay. Okay, now I'll repeat the second point for Jyoti Kumari. So we have discussed the rules to draw the resonance structure. So in that, the first structure is all the resonance structure must be in the Lewis form. Lewis structures you might have studied in your chemical bonding lesson. And coming to the second point, always the electron move from higher electron density to lower electron density region. You can see the electron is moving from higher electron density region to lower electron density. Got it? This is the second point. It is very easy, nothing to worry about it. Okay. And the third point is electron only moves and not the atoms. And the number of unpaired electrons in all the resonating structure must be same. Okay. Okay. Good. So now we can solve one question. So the question is to you on the screen. Draw all possible resonance structures of the following compound. So what is this? We have a compound which has one lone pair on nitrogen and 3 pi bonds are there and one oxygen atom is located on it. So how many resonance structures are possible? Can you guys try for it and let me know the answer in the chat box? How many structures you are getting? You're getting 2 or 3 or 4 or 5 or 6. So the number of resonance structures that is possible for this particular compound, you have to give. So try for it. I'll give you some 15 seconds. Try for it and put the answer in the chat box. Try for it. Has anyone got the answer for this? How many possible resonance structures are there? Not even a single student, huh? Okay, okay, we will discuss. Sorry, yeah. So this is the compound, right? So now the electron will move from the higher electron density region to the lower electron density region. So who is the higher electron density region here? The nitrogen, which is having the lone pair, is the higher electron density region. Got it? So that electron moves towards the adjacent bond and the double bond pi electron is moving towards this carbon. So because of this, we are getting one structure. Okay? This structure we are getting. And now this negative charge will move towards the adjacent position, adjacent sigma bond, and the pi electron which is there, it will move towards that carbon. Okay? So because of this delocalization, we are getting the third structure. Now the negative charge which is there, it will go towards carbon-carbon bond, and the pi electron which is between carbon oxygen, it will break down and it will move towards the oxygen. So because of this, we are getting one more structure. Got it? So these are the 4 resonance structures. Did you all get this? Or if you have got any other structure apart from this? So the number of possible resonance structures for the given compound is 4. So in the question, in your exam, you can get question like this. So how many possible resonance structures are possible for the following compound? So like this, you have to do the resonance structure and you have to select the correct option which contains numbers. Okay. So this is about the resonance. Now, let me go with the relative stabilities of resonance structures. Relative stabilities of the resonance structures. Relative stabilities of the resonance structures. Now, which resonance structure is more stable? So we have seen 4 resonance structure for the previous compound, right? So among this 4 compound, among this 4 structure for that compound, which is more stable? So for that we need to know some points, right? So now we are going to see those points to find out which structure is more stable. So you can see the neutral or the non-polar resonance structure is more stable than a charged resonance structure. Got it? Neutral is more stable than charged. Now, for example, let me take this. So this is the first structure. Now, if I shift the electrons, I'll get this structure, right? I'll get the second structure. Now you can see the first structure is neutral. There is no plus minus charge in it. But the second structure contains one positive and negative charge. Now you tell me which structure is more stable. the first structure is more stable because it is neutral. Got it? This is the first rule to find out the stability. Now the second point is the resonance structures having complete octet is more stable than the resonance structures having incomplete octet. What is meant by octet? If an atom contains 8 electrons around it, then that particular system is octet. Okay. Now you see here in this system. So the first structure you can see. Each atom, if you check, they will have 8 electrons around it. Let me do with one atom for you. I'll take this carbon. It is having 2 carbon-carbon bond and carbon-hydrogen bond. Now it is having, this carbon is having 4 bonds around it, and each bond will have 2 electrons in it. Now the total number of electrons around this carbon will be 8, right? Like this, you can check with each atom present in that compound. You will get 8 electrons in it. Means the first compound has attained octet. Okay. Now seeing the second compound, you see here. Let me take this carbon. Okay, it is a carbocation. It is a carbocation which we have discussed in the last class. Now we have only one hydrogen, right? We have one hydrogen there. We don't have 2 hydrogen because it is a carbocation. One hydrogen is not there. Okay. Now around this carbon we have only 3 bonds, right? So 3 bonds means how many electrons? Only 6 electrons. Already while discussing the carbocation, I have told you that there will be only 6 electrons around the carbocation, right? So now it is not 8. So that particular system or the carbon is having incomplete octet. It is having incomplete octet configuration. So because of that particular incomplete octet configuration of the second compound, the first compound is more stable than the second. Okay. Now coming to the third point, the negative charge on positive charge on less electronegative atom and negative charge on more electronegative atom is more stable. Okay. Just a second. Yeah. The positive charge on the less electronegative atom and negative charge should be on the more electronegative atom is more stable. So you can see this as an example. So see here, I have given 2 structures for you. Now in the first structure, the negative charge is on carbon and the positive charge is on nitrogen. And in the second structure, positive charge is on nitrogen, negative is on oxygen. Now you tell me which is more stable. For that, you should know which atom is more electronegative. Okay, electronegativity concept you might have studied in your periodic classification of elements lesson, right? Can you tell me which atom is more electronegative among carbon and nitrogen? Among carbon and nitrogen, which is more electronegative? Carbon or nitrogen? Can anyone tell me which is more electronegative among carbon and nitrogen? Try for it. Try for it. Guys, which atom is more electronegative among carbon? Yeah. Yeah, yes, very good, Anjanashree and Bharat. It is nitrogen, right? It is nitrogen which is more electronegative. Good. Good, Jyoti Kumari. Good. So, the more electronegative atom among the carbon and nitrogen is nitrogen. Who is the first most electronegative atom in the whole periodic table? Who is the first most electronegative element in the whole periodic table? Do any of you know the answer for this question? Which is more electronegative? Which atom is more electronegative in the periodic table? Chlorine? No. First most electronegative. Very good. Fluorine. Yeah. Jyoti Kumar, you have tried. But chlorine is also electronegative. But the first most electronegative is fluorine. Good. Fluorine is the first most electronegative. And the second most electronegative is oxygen. The third most electronegative atoms are nitrogen and chlorine. Okay. So these 4 elements, you should be knowing about this. You should not forget. First most is fluorine, second is oxygen, third comes your nitrogen and chlorine. Now coming to nitrogen and carbon, nitrogen is the most electronegative. But you see, positive charge is located on more electronegative atom. But in the second case, oxygen is more electronegative than nitrogen. So negative charge is located on oxygen and positive is located on the less electronegative nitrogen. So the second structure is more stable than the first. Got it? So these are the first 3 points. So first thing is about the neutrality. Second is about the octet. Third is about the electronegativity. Got it? So hope this part is clear for you. Then I'll go for the fourth point to find out the stability. That is distance. This point is about the distance. Lesser the distance between the unlike charges. What is unlike charges? The plus and minus, positive and negative charges. Okay. So lesser the distance between the positive and negative charge, or more the distance between the similar charge, more will be the stability. More will be the stability. What is the meaning for this? If you're having a positive and negative charge in your compound, then the distance should be very less between them. If you're having 2 positive or 2 negative charge in your compound, then the distance should be more. If these two are the cases, stability of the compound is more. So I'll show you an example. So you can see here. Now among these two structures, so these two structures contains unlike charges, right? One is positive and another one is negative in each compound. Now, which compound is more stable? Compound 1 or compound 2? Can you give me the answer? Yes, good. Compound 1 is more stable because unlike charges, distance should be very less, right? So here the distance is very less, whereas here the distance is very more high. So the first compound is more stable. Got it? And the next point is about the resonance energy. So what is meant by resonance energy? It is the energy difference between the most stable resonance structure and the resonance hybrid. RH means resonance hybrid. I'll tell you what is resonance hybrid. Okay. Now, the more stable the resonance structure, more contribution to resonance hybrid. So let me take this particular structures as an example for you. Now you can see there are 2 compounds. The first compound is cyclohexane and the second compound is benzene. Right? The first compound is what happened? Yeah, this first compound is cyclohexane and the second compound is benzene. So in cyclohexane, there is no delocalization of electrons, right? Because there is no pi electrons. But in case of benzene, we have 3 pi electrons and the delocalization of electron occurs. And what I'll get from here? I'll get one more resonance structure from here, which looks like this. And there are 2 resonance structures for this benzene. Okay. So now the resonance structures are more. Resonance structures are more. And if I want to draw the resonance hybrid for this benzene, I will be drawing the structure like this. So I'll be drawing with the dots. I'll be drawing with the dots, or I can put a circle also. I can put a circle. So the circle or this dot represents the delocalization of the pi electrons over the 6 carbon atoms. Got it? Delocalization of pi electrons towards the all 6 carbon atoms. So these 2 structures are called as resonance hybrid. It is called as resonance hybrid. If your resonance structure is more stable, then more contribution to the resonance hybrid happens. The first case, there is no resonance structure itself. Then how come to talk about the stability of resonance structure? That is not possible, no? So, you can see that the benzene has the more contribution to the resonance hybrid. Now coming to the mesomeric effect or resonance effect. Now I'll come to the resonance effect. So far we have discussed about the resonance. Now I'll tell you what is resonance effect. Resonance effect is otherwise called as mesomeric effect. The other name for resonance effect is mesomeric effect. Okay. Now the displacement of electron in a molecule through resonance is called as resonance effect. Displacement or delocalization. Okay. Through resonance is called as resonance effect. It has 2 names. One is mesomeric and the other one is resonance. And there are two types of resonance effect. One is positive resonance effect or positive mesomeric effect, and the other one is negative resonance or negative mesomeric. Like inductive, we have studied about inductive effect, no? So like that, we have two different types of effect here also. So first, we will discuss about the positive resonance effect, and then we will come to the negative. So coming to positive, so what is positive resonance effect? The system which donates electron to the carbon chain. The system which donates electrons to the carbon chain are called as positive resonance groups. And the compound which contains positive resonance group, it will exhibit the positive resonance effect. Got it? Here the electron distribution, electron donation will be to the carbon chain. Got it? And the attached atom has at least one lone pair or extended conjugation with the pi bond. I'll show you an example. So you can see here. So what is there? We have a compound and the name of this compound is phenol. And I have an atom with the two lone pairs. Since it is a phenol, oxygen usually has two lone pairs. So in this compound, we can find two lone pairs. So usually there should be at least one lone pair in your compound. Or extended conjugation. Extended conjugation means your alternative pi bond containing system. Got it? Now what happens? The electron will move from oxygen to the sigma bond, carbon oxygen bond, and the pi electron will move towards that carbon. So because of this, we get a structure like this. Got it? Oxygen is gaining the positive charge, and since electrons are moved towards the carbon, we are getting a negative charge here. Now this particular negative charge will get delocalized to the other carbon, to its adjacent system. So the electron shift occurs like this, and we get a third structure. Now this particular electron which has got delocalized, it will go here, and this will move towards this carbon. Okay. So we get a fourth structure like this, and this particular electron, it will come here, and the pi electron which is between oxygen and carbon, again it goes towards the oxygen to give the fifth structure. Got it? Now what is happening? The electrons from OH is being donated to the phenyl ring, to the carbon chain, we can say, to the ring or the carbon chain. Electron donation is happening to the carbon ring or carbon. In carbon chains also the donation happens. So what is happening here? This group is called as electron donating group. So it is called as the positive resonance. It is called as the positive resonance effect because OH is a plus R group. Okay. Now coming to the minus R group, electrons will get withdrawn from the carbon chain. Withdrawal of electron from the carbon chain is called as minus R effect. Now here the attached atom has pi bond. There, what is the condition? We should have at least one lone pair, right, or extended conjugation. Here, the system or the attached atom should have at least one pi bond with more electronegative atom. Okay, let's see an example. So I have taken nitrobenzene as an example for you. Now what is going to happen is the pi bond from the ring is now going to move towards the more electronegative atom, nitrogen. Okay. And the very most electronegative atom in the compound is oxygen. Right. So what this oxygen will do? It will pull or it will take all the electron density which is there on this nitrogen towards itself. So again, the pi electron between NO is getting shifted towards the terminal oxygen. So because of this particular electron shifting, we get one resonance structure. Since this particular electron is moving towards carbon-nitrogen bond, we get a positive charge here. Now what happens? Now we get a positive charge, and to help this particular carbocation and this electron, this pi electron will move towards that carbon-carbon bond. Got it? So we get one structure. And to help the last carbocation, this carbocation and the adjacent pi electron is coming to that to give this structure. Now, to neutralize this molecule, the pi electron again comes back to give back this structure. Okay. So in the entire process, what is happening? We have 5 resonance structures, but the electrons are moving away from the ring. Electrons are moving away from the ring. Or I can say that the nitro group, this NO2 group, is withdrawing the electron from the phenyl ring. In the last case, OH has donated the electron, so it is called as plus R group. Now NO2 is withdrawing the electron from the ring, so it is a minus R group. Okay, so it exhibits the minus or the negative resonance or mesomeric effect. Got it? Now we should know who are the plus R groups and who are the minus R groups, right? Then only we can say that this particular structure or this particular group will withdraw the electron or this group will donate the electron. Then only you can draw the resonance structure. So I'll give you a list of plus R group and minus R group on the screen. You can take the screenshot of it or you can note it down. So you can see the plus R groups are OH, alcohol, amines, NH2, tertiary amine, and OR, it is ether, ester, amide, and alkynes. All these are the groups which donates the electron to the ring. Okay, and coming to minus R group, they are nitro, and the nitrogen with positive charge, tertiary nitrogen with positive charge, sulfonic acid, CF3. CF3 is electron withdrawing because of the 3 more electronegative fluorine atoms. Okay, fluorine is more electronegative, right? So what is electronegativity? What is electronegativity? The tendency of attracting the shared pair of electrons towards itself, right? So fluorine containing compounds always withdraws the electron. So that's why CF3 is acting as a minus R group. And CCl3 is also same. Fluorine is also more electronegative. Like CF3, CCl3 is also your minus R group. And all the carboxylic acid, aldehydes and ketones, they are minus R group containing minus R groups. Okay. Now, this particular mesomeric effect will act only in ortho and para position. You can find the effects only in ortho and para position. Okay. Let me show you the previous case. You can see the positive charge is getting delocalized at ortho and para. I already told you what is ortho and para and meta, right? What is ortho? Ortho means adjacent to the group which is attached to the ring. And what is meta? Alternative position to the group attached. And what is para? Opposite to the group which is attached to the ring. Okay. Now you can see the positive charge is delocalizing on the ortho and para position. In the last case also you can see the negative charge would have delocalized only at ortho and para, not at meta. So mesomeric effect is acting only at ortho and para position. This is the very important point. You have to take a note of it. Okay. So this is about the mesomeric effect. And now let us see the applications of mesomeric effect. Okay. What are the applications? So from the mesomeric effect, what and all we can find out. So the first thing is we can find the stability of the carbanion. What you can find? You can find the stability of carbanion from the mesomeric effect. Okay. So who are carbanions? They are electron-rich compounds, right? They are electron-rich compounds. Now, how to determine the stability of a carbanion? You can determine by seeing the electron density. If the electron density is more, then the stability is very less. If the electron density is less, stability is more. They are inversely proportional. Okay, electron density is inversely proportional to stability, but it is directly proportional to the stability is directly proportional to the negative mesomeric effect. Negative mesomeric effect and inversely proportional to the positive mesomeric effect. Okay, I'll show you a question for you. Now we are going to compare the stability of the following anions. Okay, so you can see 3 compounds. You can see 3 compounds. So in all the compounds, we have a phenyl ring which is attached to CH2 minus. So this is our carbanion. This is our carbanion. And in the first compound, you can see CH3 group is attached. So who is the CH3 group? It is an alkyl group, right? Alkyl groups are plus M group. Alkyl groups are plus M group. The group which donates the electron to the ring. The group which donates the electron to the ring. Okay. And in the second compound, we don't have any group. We don't have plus or minus R group. And coming to the third compound, you can see nitro group is present. Nitro group is a minus M effect. Nitro group is minus M group. So what happens here? The stability of the compound which has minus M group is more. Okay. So that's why the minus M group is directly proportional to stability, but the plus M groups are inversely proportional to stability. So if you are having the plus M group in your compound, then it is the least stable. Got it? The one which is having the electron withdrawing group in the compound, then that compound is more stable. Only in case of carbanion. Only in case of carbanion. Okay? Carbanion with the electron withdrawing group in it is more stable. That is the concept you are getting from it. So in the question paper, they can give 3 compounds like this, and they will ask you to arrange the given compounds in the increasing order of stability or decreasing order of stability. So if you are finding any negative charge, if you are finding any carbanion in your system with the electron withdrawing group attached to it, then select that option as first. Okay. Then the system which contains no group, and then comes your positive, the electron donating group containing compound. Okay, this is only for carbanion. You have to follow the stability like this. Then the second application is you can find out the acidity of reagents. How to find out the acidity of reagents using mesomeric effect? Acidic strength is directly proportional to Ka. Ka means acid dissociation constant. So we will study what is acid dissociation constant and all in our chemical equilibrium lesson. Okay, don't worry about it. So in the exam, if they are asking question using Ka value, they will give you the value. They will give you the value in the question. And if they are giving the values in the question for 3 compounds, then the one which is having more Ka value is more acidic. The one which is having the highest Ka value is more acidic, because acidic strength is directly proportional to Ka. Okay, this is what you keep in your mind for now. Then I'll teach you in the chemical equilibrium lesson about the Kas. Got it? And it is directly proportional to minus M and inversely proportional to plus M again. Now let us compare the acidic nature of the given compounds. So I'll give you 4 compounds. I'll give you 4 compounds. 4 compounds are there for your screen. And now we are going to find out which is more acidic in nature. Can anyone guess which is more acidic? Which compound is more acidic among the 4? 1 or 2 or 3 or 4? Can you apply this concept and tell me which compound is more acidic? Leave this Ka value. We don't have Ka value in this question, but we have minus M group and plus M group. No? Can you guess which is more acidic? Acidic strength is directly proportional to minus M group. So the compound which has minus M group is more acidic in nature. Now can you guess? Yes, Anjana Sri. Very good. It is compound 4. It is compound 4. Yes, good. So in case of compound 1, what do we have? We have CH3. CH3 is a plus M group. And in case of second compound also, we have CH3. But that second compound CH3 is attached at the meta position. So they will not they will not act mesomeric effect. They will act only the inductive effect. What is inductive effect? Polarization of sigma bond, right? So that type of effect is followed here. Since CH3 is an electron donating group, it will donate the electron to the ring. So it is plus I group. Now coming to compound 3. So between compound 1 and 2, compound 2 is more stable, more acidic. Now coming to compound 3, you can see nitro group at meta position. So meta position should not have mesomeric groups. So nitro group is considered as minus I group here. So electron density is more. Electron density is very less because nitro group will withdraw all the electrons from the ring. So which makes the ring more electron deficient. The more electron deficient compounds are called as acids, right? So this system is more electron deficient in nature because of the withdrawal of electron by NO2 group from the ring. So the ring becomes electron deficient in nature. That's why it is more acidic. Okay, that's why it is more acidic compared to the second compound. Now coming to compound number 4, we have minus M group because the group is located at para position. So the resonance effect will act. So because of this minus M group at para position, that is more acidic in nature among the 4 given compounds. Got it? Any doubt you have? Any of you have any doubt from the acidity? No doubt? Okay. Fine. So since you all have joined very late for today's class, it's already 3:59 now. I'll stop here. So there are some more applications for mesomeric effect. So those applications I will discuss in the next class, and then we will move on to the next topic, aromaticity topic. Okay. So in today's class, we have seen what is resonance and the resonance effect and the resonance groups, plus R and minus R groups we have discussed, and 2 applications. So what are those 2 applications? What is the first application? What is the first application we have seen, students? Yeah. First one was stability. We are able to find out the stability of a compound from resonance effect, and we are able to find out the acidity of a compound using the resonance effect. And some more applications are there. Those we will discuss in tomorrow's class. Okay. Try to join on time from tomorrow onwards. Okay. Thank you. Thank you so much. Thank you so much, students, for listening to the class.